Imagine the world is finally waking up. The ice has been retreating for thousands of years. Glaciers that once buried entire mountain ranges are pulling back, melting into rivers and lakes and rising seas. Forests are creeping northward where tundra used to be. Temperatures are climbing. Animals are spreading into new territories. Humans are moving, exploring, settling into a world that is finally, slowly, becoming livable in ways it hadn't been for tens of thousands of years. The last great ice age is ending, and the planet is exhaling. And then, without warning, it stops. Around 12,800 years ago, the climate just flips. Not slowly, not gradually over millennia the way these things are supposed to work. Quickly, dramatically. Within a matter of decades, possibly even less, temperatures in some parts of the northern hemisphere plunge by as much as 10 to 15 degrees Celsius. Glaciers that had been retreating begin advancing again. Forests that had been spreading start dying back. The world that had been warming for thousands of years snaps back towards something that looks a lot like the ice age everyone thought was ending. And it stays cold for roughly 1,200 years. Scientists call this event the Younger Dryas. The name comes from a small flowering plant called Dryas octopetala, a cold-loving wildflower that suddenly reappears in the fossil pollen record across Europe right at this moment. A flower that had no business blooming in warming landscapes starts showing up everywhere. It's a tiny botanical clue pointing to something enormous. And that is really the beginning of one of the most fascinating and still contested mysteries in all of climate science. Here's what makes it so strange. Climate change at the scale of ice ages is not supposed to happen this fast. The slow rhythm of glacial and interglacial cycles is driven by subtle wobbles in Earth's orbit, changes that unfold over tens of thousands of years. The whole system is massive, and massive systems have inertia. They resist sudden change the way a huge ship resists turning quickly. And yet here is the evidence, preserved in exquisite detail in multiple independent archives from around the world, that the climate did something almost violent around 12,800 years ago. Something triggered a reversal so abrupt that it shows up as a hard line in the geological record rather than a gradual slope. What could do that? What could grab a warming planet and yank it back toward cold in the span of a human lifetime, maybe even faster? That is the question sitting at the center of everything we're going to explore. And the honest answer, right from the start, is that scientists don't fully agree. There are serious competing hypotheses. There is genuine evidence on multiple sides. And the debate is still very much alive, which is actually what makes this story worth telling. Because the uncertainty here isn't a weakness. It's a window into how science works when it's wrestling with something genuinely hard. Before we get into the theories, it helps to understand how we even know any of this happened. The Younger Dryas left marks on almost everything. Ice cores drilled from Greenland contain annual layers of compressed snow going back hundreds of thousands of years, and the chemical signatures in those layers change dramatically right at 12,800 years ago. Oxygen isotope ratios, dust concentrations, even the types of particles trapped in the ice, all of them shift suddenly and clearly. It is like reading a book that is going along normally, and then suddenly every page turns a different colour. Ocean sediments tell a similar story. The tiny shells of microscopic marine creatures called foraminifera record the temperature and chemistry of the water they lived in. When scientists pull cores from the seafloor, they find those shells changing abruptly at the same moment. The ice cores do, telling us the oceans felt it too. Not just in one place, across the North Atlantic, across much of the northern hemisphere. On land, pollen preserved in lake sediments records the changing vegetation with remarkable precision. Trees disappear. Cold-adapted plants return. In some records, the transition happens so fast that it is essentially instantaneous at the resolution scientists can measure, which is already in decades rather than centuries. And then there is the archaeology. Right at this moment, human cultures that had been spreading and thriving across multiple continents seemed to undergo profound disruptions. People change where they live, how they live, what they hunt, what tools they make. The Younger Dryas doesn't just show up in ice and mud and pollen. It shows up in human history. All of that evidence, layered on top of each other from independent sources, all pointing to the same moment, is what makes the Younger Dryas one of the best documented events in all of prehistoric climate science. And also one of the most puzzling over the next sections. We're going to walk through the main explanations that have been proposed, from collapsing ocean circulation to catastrophic floods, from extraterrestrial impacts to volcanic eruptions to subtle shifts in how Earth absorbs sunlight. Some of these ideas have strong support, some are deeply controversial. Some might work together. The goal isn't to hand you a clean answer, because a clean answer would not be honest. The goal is to show you what the evidence actually says and where it leaves us. But before we go any further, I want to ask you something. Drop a comment and tell me where you are right now and what time it is where you're listening. Are you in Tokyo winding down for the night? Somewhere in the middle of Europe just before dawn? Maybe it's late afternoon in California or the middle of a sleepless night in Sao Paulo. I check these comments, and every time it is genuinely surprising. This spread of people across time zones, all sitting with the same strange history. It's one of my favourite things about making these. So tell me, and then settle in, because 12,800 years ago, the world got a very cold surprise, and we're just getting started. To understand why the Younger Dryas was such a shock to the system, you need to know what the world looked like in the millennia before it happened. Because the cold snap didn't arrive in a vacuum. It interrupted something. It broke a trajectory. And to appreciate just how strange and violent that interruption was, you have to feel the world that existed before it. Go back about 26,000 years. The Earth is in the grip of what geologists call the last glacial maximum, the peak of the most recent ice age. And the word peak really doesn't do it justice. Ice sheets stretch across North America in a continuous frozen mass that buries everything from modern-day New York to the Arctic in ice, sometimes 2 or 3 kilometers thick. You could stand on that ice and not see land for 1,000 miles in any direction. In Europe, ice covers Scandinavia entirely and pushes deep into what is now Germany, Poland and Britain. In the southern hemisphere, Antarctica wears an even larger version of its current ice cap. Mountain glaciers that today are retreating visible traces of a colder time were then massive rivers of ice carving valleys and grinding bedrock down to dust. And because so much of the world's water is locked up in those ice sheets, the oceans are dramatically lower, not a little lower, roughly 120 meters lower than today. Which means the coastlines of every continent look completely different. What is now the shallow seabed between Britain and Europe is dry land, a broad plain with rivers running through it. Australia and New Guinea are connected. The islands of Southeast Asia are stitched together by exposed continental shelves into something almost unrecognizable compared to a modern map. People and animals are moving across land bridges that don't exist anymore, following coastlines that have since disappeared beneath the waves. The world is colder, drier, and in many ways larger, at least in terms of accessible land. Then, starting around 19,000 years ago, something begins to shift. Earth's orbital geometry, the slow wobble and tilt of the planet as it travels around the sun, begins delivering slightly more solar energy to the northern hemisphere during summer. The change is subtle, it's not dramatic, but it is enough to start tipping the balance. Ice that had been accumulating for millennia begins to melt more than it gains each year. Slowly at first, then more noticeably, the great ice sheets begin to retreat. This process is called deglaciation, and it's important to understand how it's supposed to work because the Younger Dryas is so striking, partly because of how different it was from the expected pattern. Orbital forcing, the slow dance of Earth around the Sun, operates on timescales of tens of thousands of years. It is not a sharp switch, it is a dial being turned by an extremely patient hand. The expectation, based on how ice ages had ended before, was that warming would proceed unevenly but generally in one direction. Ice would melt, sea levels would rise, forests would expand. Things would warm up, interrupted here and there by slower periods, but not reversed outright. The inertia of the system, the sheer mass of ice and ocean water involved, should have prevented anything too sudden. And for a while, that's roughly what happened. Between about 19,000 and 14,700 years ago, the ice sheets retreat, sea levels begin to climb, and temperatures across much of the northern hemisphere trend slowly upward. It's not smooth. There are pauses, regional variations, moments where things slow down. But the general direction is clear. The Ice Age is winding down. And that alone would have been enough to transform the world over the following millennia. Then, around 14,700 years ago, something accelerates the warming dramatically. Temperatures in Greenland, based on ice core evidence, jump by roughly 10 degrees Celsius in what appears to have been an astonishingly short time, possibly just a few decades. This is the beginning of what climate scientists call the Bulling-Olerode warm interval, named after two locations in Denmark, where the evidence was first clearly identified in ancient lake sediments. The Bulling and Olerode were originally identified as slightly distinct subphases, but they represent broadly the same extended period of warmth, running from roughly 14,700 to about 12,900 years ago. During the Bulling-Olerode, the world genuinely looks like it's warming its way out of the Ice Age for good. Forests spread rapidly across Europe. Birch and pine pushed northward into regions that had been cold steppe and tundra. Animals follow the vegetation. Reindeer herds that had dominated the landscape of southern Europe begin shifting northward as the climate they depended on migrates with them. In North America, temperatures climb. In parts of the Middle East, the warming and increased moisture create conditions that will eventually, several thousand years later, allow the development of agriculture. The human populations that have been living as highly mobile hunter-gatherers across multiple continents begin settling in ways that look slightly more permanent, following resources that are suddenly more predictable. But here is something easy to miss if you look at the big picture too casually. Even during this overall warming, regional climates are not moving in lockstep. The northern hemisphere as a whole is warming, yes. But some areas are warming faster than others. Some are actually experiencing more variable conditions. Not a smooth upward trend, but oscillations, good years and bad years, wet decades and dry ones. Parts of the tropics seem to be responding to the orbital changes differently than the high latitudes. The monsoon systems of Asia and Africa are shifting, and not always in ways that simply parallel the northern hemisphere temperature story. Climate, even in aggregate, is not a single dial turning in one direction. It's more like a vast orchestra where most instruments are moving toward the same key, but the timing is never perfectly synchronized. This matters because it tells us something important about the system we're dealing with. Even during a period of clear, documented, large-scale warming, the climate is capable of producing regional surprises, local reversals, and unexpected variability. The general trend is real, but so are the complications within it. There is also a brief cold interruption partway through, around 13,900 years ago, called the Younger Dryas, which is a smaller and less severe cold snap that sits inside the Bulling-Olerode period. It's a reminder that the deglaciation wasn't perfectly monotonic even before the Younger Dryas. The system had wobbled before, but the Younger Dryas was relatively mild and brief compared to what was coming. People at the time, had they been able to perceive it at the scale of a human lifetime, might have noticed a few harder winters, a slight retreat of the forests, then a return to warming. The Younger Dryas is a footnote. What came next was not. by roughly 12,900 years ago, the Bulling-Olerode warming has been going on for around 1,800 years. Sea levels have risen substantially. Ice sheets have lost enormous amounts of mass. The trajectory seems established. If you could somehow survey the world at that moment and extrapolate forward, you would reasonably predict continued warming, continued ice retreat, and a gradual but steady transition into the warmer, wetter interglacial world that scientists call the Holocene. Every signal in the planetary system points the same direction, which is exactly what makes what happens next so difficult to explain through ordinary means. Because the Younger Dryas doesn't sneak up on a planet that was struggling. It strikes a planet that was succeeding at getting warmer. This is the crucial context. The question isn't just what caused a cold event. The question is what was powerful enough to reverse a well-established warming trend, overwhelm all the orbital and atmospheric momentum that had been building for thousands of years, and do so fast enough to show up as a nearly instantaneous line in the geological record rather than a gradual slope. Orbital forcing, the mechanism that had been steadily driving the warming, works on timescales of tens of thousands of years. It cannot produce a climate reversal in decades. Something else had to have intervened. Something operating on an entirely different timescale, with an entirely different kind of leverage over the climate system. Whatever that something was, it had to be powerful enough to override inertia that had been building since the glacial maximum. Powerful enough to work fast, and powerful enough to sustain a near-glacial climate for 1,200 years before finally releasing its grip. The world in the centuries before the Younger Dryas was not a fragile, barely warming world teetering on the edge. It was a world in the middle of genuine and dramatic recovery. That's what makes the interruption so striking, and that's what makes the question of its cause so hard to answer, with a simple explanation. Because whatever happened, it didn't nudge the climate. It grabbed it. So how do we know that this climatic grab actually happened, and that it wasn't just a long, cold run of bad weather in a few unlucky places? To answer that, you have to follow the trail of evidence into places where time is recorded, layer by layer. Places where every year leaves a mark, whether it's a snowflake, a grain of dust, a ring of wood, or a drifting pollen grain settling into the quiet bottom of a lake. The most famous records come from deep inside the Greenland ice sheet. If you drill a narrow cylinder of ice 2 or 3 kilometers down, what you're really doing is pulling up a frozen time capsule. Each year, snow falls, gets buried by the next winter's snow, and slowly compresses into ice. Trapped inside that ice are tiny bubbles of ancient air, specks of dust, traces of sea salt, volcanic ash, and subtle shifts in the ratio of heavy to light oxygen in the water molecules themselves. That last part, the oxygen isotope ratio, is one of the main thermometers of the past. In colder periods, more of the lighter isotope, oxygen-16, ends up locked in ice sheets and seawater, and the vapour that falls as snow becomes slightly enriched in the heavier oxygen-18. The exact balance between the two is sensitive to temperature. So when scientists measure sudden jumps in these isotopes down an ice core, they're seeing abrupt changes in the climate of the past. In Greenland, the Younger Dryas shows up as one of those jumps. At the end of the Bulling-Olerode, the isotope values that had been tracking a warm interstadial climate suddenly swing back toward the colder ice age pattern, not over thousands of years, over what appears in some cores to be the span of a human lifetime or less. In the layers corresponding to that transition, the trapped air bubbles change too. Greenhouse gas concentrations that had been rising during deglaciation flatten or dip. At the same time, dust levels in the ice increase, hinting at a world with stronger winds, drier continental interiors, and more exposed soil. Chemical clues, like changes in sodium, calcium, and nitrate, tell us something about shifts in sea spray, desert dust, and even biological activity. Put together, these signals sketch the same story. A quick lurch from a relatively warm, moist atmosphere back into something much more like a glacial climate. And this isn't just a curiosity in one core. Multiple ice cores from different parts of Greenland show the same pattern, the same step, at roughly the same depth. Whatever happened around 12,900 years ago was not local to one patch of ice. It was something that affected the entire North Atlantic climate system. If Greenland is the loudest voice in the room, Antarctica is the quiet one in the back saying, "Yes, but it's complicated." When you look at ice cores from the Antarctic ice sheet, you see deglaciation. You see the overall transition from full ice age to interglacial. You see structures that can be matched roughly to events in the north. But the timing and intensity aren't a perfect mirror image. During the Younger Dryas interval in the north, Antarctica doesn't plunge back into deep glacial cold at the same moment. Instead, it shows a more muted response, sometimes even a tendency toward gradual warming while Greenland is shivering. The temperature swings are smaller in amplitude, and the transitions are more drawn out. This difference is one of the reasons climate scientists don't just talk about the Earth getting colder or warmer, as if it were a single uniform object. The two hemispheres are connected by ocean currents and atmospheric circulation, but they don't always move in lockstep. There's a kind of seesaw behaviour. When deep water formation in the North Atlantic weakens, heat that would have been carried north can linger in the southern oceans instead. Greenland cools sharply. Antarctica responds differently, on a different schedule. So the Antarctic ice cores confirm that something global is going on in the deglaciation story, but also remind us that the Younger Dryas is strongly expressed in the north and more subdued in the south. The planet isn't flipping a single switch. It's rearranging heat, moving energy and moisture around a three-dimensional fluid system. Ice cores, though, are only part of the evidence. If all we had were frozen cylinders from Greenland and Antarctica, you might wonder whether these abrupt shifts were somehow artifacts of polar dynamics, limited to the high latitudes. To test that, you need independent clocks from different environments, built from entirely different materials. One of those clocks is carved in wood. Trees in temperate regions add a ring of new growth each year. The width and density of those rings respond to conditions like temperature and moisture. In some species under the right climates, the pattern of wide and narrow rings becomes an annual heartbeat that can be matched and overlapped from living trees back into dead wood, extending a continuous record thousands of years into the past. When dendrochronologists, tree ring scientists, line up sequences from old preserved logs in Europe or North America, they see disturbances around the onset of the Younger Dryas. Periods where growth slows, rings narrow and the trees record years that were suddenly harsher than the ones before. These don't give a global temperature number, but they show that around 12,900 years ago, conditions changed on land in ways consistent with a return to colder, more stressful climates. Another set of clocks rests quietly at the bottoms of lakes. In some lakes, especially those in cold or seasonally stratified environments, sediments are deposited in neat, couplet layers called varves. A single light-dark pair often represents 1 year, coarse material in one season, fine in another. Layer by layer, they build up a chronology as precise as a stack of pages in a book. When those varved sediments from Europe and North America are sliced and examined, you can often count the years across the Younger Dryas boundary, almost like counting rings in a tree. The layers shift from those characteristic of warmer, more productive lakes, rich in organic material, with certain types of algal remains, to layers dominated by clays and silts washed in from more eroding, less vegetated catchments. In some sequences, you can literally count roughly 1,200 annual layers with cold state characteristics before the system flips back into layers that look more like early Holocene conditions. Caves offer yet another kind of record. Inside limestone caverns, dripping water deposits thin layers of calcite on stalagmites and stalactites. The chemistry of that calcite, including oxygen isotopes and trace elements like magnesium and strontium, records changes in rainfall, temperature, and the source of moisture feeding the cave system. Speleothems, these cave deposits, from places as far apart as China, the Middle East, and Europe, show distinct shifts around the Younger Dryas. Monsoon strength weakens or reorganizes. Wet periods give way to drier ones, or vice versa, depending on the region. What matters is the timing. When these independent cave records are carefully dated using uranium-thorium methods, their transitions line up, within dating uncertainties, with the onset and end of the Younger Dryas as seen in the ice. Wood, mud, and stone are all telling a similar story about the timing and pace of the event. Then there is the quieter, but equally compelling record left by plants. As climates shift, so do ecosystems. Trees, shrubs, and grasses don't stay put out of habit. Their seeds ride the wind, birds and mammals colonizing new ground wherever conditions allow. Over centuries, forests can advance northward, or retreat upslope, tracking the climate zones they prefer. In bogs and lakes, the rain of pollen grains from surrounding vegetation settles into the accumulating sediments. Pollen grains have distinctive shapes and structures. Under a microscope, a trained palynologist can tell a pine from a birch, a grass from an oak, simply by looking at the tiny shells those plants left behind. Across Europe, the Near East, and parts of North America, pollen records show the Younger Dryas as a sharp reversal in vegetation trends. During the Bowling-Oller Road, tree pollen like birch and pine increases rapidly as forests invade former tundra and steppe. Then, right at the Younger Dryas boundary, tree pollen declines and pollen from cold-tolerant grasses, herbs and shrubs jumps again. In some cores, you can see the transition over just a few centimeters of sediment, representing only a handful of decades. Plant macrofossils, the larger bits, like seeds, leaves, and needles that sometimes preserve in waterlogged sediments, tell a similar story in more local detail. In a peat bog that had been steadily accumulating remains of forest plants, you suddenly find a layer dominated by dwarf shrubs and tundra species. That doesn't happen if climate drifts slowly, generation after generation, across a threshold. It looks like a cliff, not a ramp. All these records together lead to an uncomfortable word for a system as massive as Earth's climate: abrupt. In everyday language, abrupt can mean seconds or minutes. In climate terms, abrupt means something different, but still shockingly fast. When scientists say the Younger Dryas onset was abrupt, they mean that major hemisphere-scale shifts in temperature, wind patterns and ecosystems unfolded in less than a human lifespan. Some estimates based on Greenland ice cores suggest that the main cooling step, at least locally, may have occurred in a decade or two. On a planet where ice sheets take millennia to build, and ocean basins take millions of years to open and close, a decade is nearly instantaneous. It is as if you were watching a glacial landscape crawl and creep for thousands of years, only to see, suddenly, an invisible hand yank the thermostat down, while most people who were alive at the start of the change were still alive to feel its consequences. That is what makes the Younger Dryas so striking in the geological record. Not just that it happened, not just that it was cold, but that so many independent lines of evidence, bubbles in polar ice, rings in ancient wood, laminations in lake mud, dripstones in caves, and the ghostly shapes of long-dead pollen grains, all converge on the same conclusion. Something grabbed the climate system. It did so quickly enough that entire forests, animal communities and human groups had to scramble to adjust within the span of a few generations. And it held on for more than 1,000 years. The question that still haunts researchers isn't whether this happened. The records are too consistent for that. The question is why it happened the way it did, and what exactly pulled so violently on a system that had every reason, by orbital logic, to keep on warming. To explore that, you have to move from the evidence of change to the moment of change itself. to the point in time when, in those ice layers and lake sediments and pollen diagrams, the lines bend sharply. The instant when the warming stops and the cold comes rushing back. If you could stand somehow on that boundary layer in the Greenland ice, the place where the isotopes jump and the dust darkens, what would it have felt like to be alive? Not in the abstract sense of a line on a graph turning downward, but in the slow day-to-day experience of people and landscapes at the very end of the Ice Age. In the centuries leading up to the Younger Dryas, the world your ancestors knew in the north was changing fast, but mostly in one direction: warmer, wetter, more hospitable. Glaciers were retreating from their maximum positions. In Europe, birch and pine forests had marched northward, following the melting ice. In North America, tundra gave way to shrublands and open woodlands along the ice margin. Rivers swollen with meltwater braided across broad plains. Then, somewhere around 12,900 years ago by our modern calendars, that sense of one-way progress faltered. In the Greenland ice, the onset of the Younger Dryas is marked so clearly that you can almost point to it with your finger. Above a certain depth, warm phase values, relatively low dust, chemistry consistent with a milder, more humid atmosphere. Below it, the return of colder phase isotope ratios, higher dust, a different balance of chemical traces. Counting annual layers in some of those cores, the main shift seems to play out over just a few decades. The exact number is debated. Some reconstructions suggest maybe 20 or 30 years for the bulk of the cooling, perhaps even less for part of it. For the people living under those skies, that's not a sudden snap in a single winter, but it is a lifetime in which the seasons grow noticeably harsher, one after another, until the pattern that seemed to promise a gentler world is gone. The temperature change was not trivial. In Greenland itself, Proxy reconstructions suggest that average temperatures fell by something like 5 to 10 degrees Celsius compared to the preceding warm phase. That's the difference between a landscape where snow cover melts fully each summer and one where it can linger stubbornly year after year. Between lakes that remain mostly ice-free in the warm season and lakes that start to freeze earlier, thaw later, and trap cold water beneath their surfaces. Across the broader North Atlantic region, the numbers look smaller, but still significant. Western Europe appears to have cooled by several degrees on average. Summers would have been shorter and cooler, winters longer and more severe. In some areas, precipitation likely decreased, forests stalled or retreated, and open, wind-swept steppe tundra reclaimed ground that had only recently supported trees. Further south and east, the story wasn't just about temperature, but about water. Monsoon systems which bring seasonal rains to large parts of Asia, the Middle East and North Africa, seem to have reorganized. Cave records from China and Oman, for example, suggest that summer monsoon strength weakened around the onset of the Younger Dryas. What that means in practical terms is fewer reliable rains, more frequent droughts, perhaps a shift in when the rainy season arrived or how intense it was when it did. In the eastern Mediterranean, some lake records and cave deposits point to episodes of drying and increased seasonality. In parts of the Levant, pollen and lake levels suggest that what had been a relatively moist forest expanding climate gave way again to more steppe-like conditions. Grass, sage, and other dry-adapted plants rebounded, where oaks and pines had started to spread. At high northern latitudes, one of the most important changes was not just in the air, but on the surface of the ocean. As the North Atlantic cooled, sea ice pushed southward. Seasonal ice that had been confined closer to the Arctic edge could now expand over a wider area of ocean, lasting longer into the spring and sometimes surviving year-round in places that had been seasonally open water. This matters because sea ice is part of a powerful feedback loop. Open ocean is dark and absorbs most of the sunlight that hits it. Sea ice is bright It reflects a large fraction of that light back into space. As more ice forms, more sunlight bounces away, which keeps the ocean's surface colder, which helps preserve and thicken the ice. It's a self-reinforcing pattern. The presence of sea ice also changes the way the atmosphere behaves. Ice-covered water evaporates less readily, feeding less moisture into the air. Cold surfaces stabilize the lower atmosphere, altering pressure patterns and guiding storm tracks along different paths. Evidence for these changes shows up indirectly in the records. Marine sediments from the North Atlantic contain more fragments of ice-rafted debris, bits of rock and sediment dropped from melting icebergs at the beginning of the Younger Dryas interval. That suggests increased export of ice from glaciated regions and more extensive cold surface waters. On land, the fingerprints of a stormier, dustier, wind-scoured world also appear. Greenland ice layers from the Younger Dryas are dust-rich relative to the preceding warm phase. The grains themselves and their chemical signatures point to continental interiors that were drier and more exposed. Without dense vegetation to bind soils, winds can lift fine particles and carry them thousands of kilometers, ultimately depositing them in polar snow. Loess, wind-blown silt, accumulations in parts of Europe and China also show changes consistent with stronger or more persistent winds at certain times during the Younger Dryas. In some regions, you see thicker, coarser layers, suggesting episodes when dust transport intensified. Even tree rings, which are local by nature, whisper of altered wind and storm patterns. Narrower rings can reflect cold or drought, but patterns of frost damage, growth interruptions, and sudden die-offs in certain regions imply not just cooler averages, but more frequent late frosts, cold snaps, and perhaps violent storms that could strip buds and branches. The atmosphere, under these conditions, likely organized itself differently than during the preceding warm phase. Jet streams may have shifted position. Winter storm tracks may have plunged further south over the Atlantic, bringing cold, dry air into Europe and steering moisture toward new targets. Blocking patterns where high-pressure systems linger and prevent normal weather progression might have become more common, locking regions into extended spells of cold or drought. Yet for all this talk of cold, it's important to remember that the Younger Dryas was not a uniform, frozen blanket thrown across the entire planet. While Greenland and much of the North Atlantic sector cooled sharply, other regions experienced subtler changes or even shifts in the opposite direction. In parts of the southern hemisphere, especially around Antarctica, the Younger Dryas interval does not show up as a dramatic plunge back into glacial values. Instead, Antarctic ice cores tend to show a slower, steadier warming trend through this period, superimposed with smaller fluctuations. The temperature difference there across the Younger Dryas is measured in a few degrees at most, and the timing of changes does not perfectly match the northern onset point. Some regions of the southern oceans may even have stored more heat during the Younger Dryas, as less was transported northward by the global overturning circulation. That surplus warmth could have influenced sea ice extent, marine ecosystems, and regional climates far from the North Atlantic. Even within the Northern Hemisphere, the pattern was patchy. The North Pacific, for example, shows evidence of cooling in some proxies, but not always with the same timing or intensity as the North Atlantic. Parts of interior Asia and western North America experienced changes that seem to reflect shifts in atmospheric circulation rather than a simple, uniform drop in temperature. In the tropics, sea surface temperature reconstructions from some regions suggest modest cooling on the order of a degree or less, while others appear relatively stable within the uncertainties of the data. What shifted more dramatically there was often the distribution of rainfall, which side of a mountain range got the bulk of the monsoon, which river basins flooded and which dried. From the perspective of people living at the time, this meant that the moment the cold returned wasn't the same everywhere. In some coastal parts of Western Europe, perhaps the first hints were a string of disappointing summers. Crops or wild plant foods that had been thriving during the bulling Olerode started to struggle. Lakes froze earlier in the year. Sea ice lingered near shorelines longer into the spring. Further south in the Levant or Anatolia, the key change might not have been bitter cold so much as unreliable rain. Springs and seeps that communities depended on became less predictable. Hillsides that had been turning to light woodland held back, remaining open, scrubby, less forgiving. In high-latitude North America, hunters tracking herds along the shrinking edge of the Great Laurentide ice sheet may have noticed that the ice was not retreating as steadily as it had before, that meltwater channels refroze more firmly each winter, that certain plants failed to colonize freshly deglaciated ground. To someone living through it, the Younger Dryas onset would not have announced itself with a name. There would be no clear signal that the event had begun. Only the accretion of small disappointments and surprises, a river that broke up later, a migration that came early or late, a valley that stayed treeless longer than expected. Underneath all those lived experiences, though, the physical system had crossed a threshold. Sea ice expansion, altered ocean currents, reorganized winds, shifting storm tracks, and changing patterns of rainfall all reinforced each other until the climate of the North Atlantic and surrounding continents settled into a new, colder configuration. Not a perfect return to the full glacial world, but a step backward in that direction, held in place for more than a millennium. To understand how such a reconfiguration could happen so quickly, and why some regions felt it more sharply than others, you have to look more closely at the machinery that moves heat around the planet. In particular at the oceans, the great, slow rivers within the sea that quietly shuttle warmth from the tropics to the poles and back again. When people talk about ice ages and abrupt climate shifts, they often picture the atmosphere doing all the work. Colder air, more snow, fiercer winds. But the atmosphere is fast and thin. It responds in days and weeks. The deep rhythm of Earth's climate, the part that can lock a pattern in place for centuries, is mostly set by the oceans. Under the choppy surface, beneath the storm-tossed waves, there are immense, slow-moving currents that behave almost like conveyor belts. They carry warm water toward high latitudes, release heat to the air, grow colder and denser, and then sink, flowing back toward the equator in the deep ocean. This global circulation is sometimes called the ocean conveyor, but in the North Atlantic it has a more formal name, the Atlantic Meridional Overturning Circulation, or AMOC. Despite the intimidating title, the basic idea is simple. In the North Atlantic, especially around places like the Labrador Sea and the seas between Greenland, Iceland and Norway, cold, salty surface water becomes dense enough to sink into the deep ocean. That sinking motion helps pull warm, relatively salty water northward from the tropics. As it travels, that warm water releases heat into the atmosphere, taking the edge off winters in Western Europe and the North Atlantic coasts. Then, having cooled and sunk, it joins the deep return flow that slowly creeps southward, thousands of meters below the surface. You can think of it like a massive three-dimensional loop. Warm water north at the surface, cold water south at depth. The strength of that loop depends on density differences. Water that is colder and saltier is heavier and more willing to sink. This is where freshwater becomes important. Fresh water from rainfall, rivers or melting ice is less salty than the open ocean. When enough of it accumulates on the surface in key regions, it acts like a lid. It makes the surface layer lighter, more buoyant, less eager to plunge downward. If the layer stays fresh and thick enough, long enough, the rate of deep water formation can slow or even stall. In the real ocean, nothing is controlled by a single switch. But the North Atlantic seems to behave as if it has a set of thresholds. Add a little extra fresh water and the system adjusts. Add a lot, especially when background conditions are already changing, and the entire pattern of circulation can reorganize. Climate scientists sometimes describe the North Atlantic as a control knob for the wider climate system, not because it dictates everything, but because it is unusually sensitive. It sits at the end of a major heat transport pathway from the tropics. It is rimmed by large ice sheets during glacial times. It receives vast amounts of meltwater from those ice sheets and from proglacial lakes that build up along their margins. Small shifts in salinity and temperature there can have outsized effects on how much heat is carried north and how much is left behind in the south. During the last deglaciation, when the Younger Dryas occurred, that sensitivity was probably heightened. Ice sheets in North America and northern Europe were melting. Gigantic lakes dammed by ice existed along their edges. Rivers were rerouting themselves across landscapes that had been crushed and reshaped by moving ice. Into this already complex setting, any extra pulse of fresh water pouring into the North Atlantic could tip the balance between vigorous overturning and a more sluggish, surface-intensified circulation. We don't have direct gauge readings of the amok from 12,800 years ago. What we do have are the sediments that quietly settled to the seafloor as all this was happening. Imagine scraping a core from the bottom of the North Atlantic and reading it from bottom to top as a timeline. Within those layered muds and oozes are the shells of microscopic organisms called foraminifera. They look like tiny coiled beads under a microscope, but they are powerful storytellers. Foraminifera build their shells from the carbon and oxygen dissolved in seawater. The exact proportions of different oxygen isotopes in those shells, slightly heavier or lighter versions of the same element, depend on the temperature and composition of the water they lived in. When scientists measure those ratios down the length of a sediment core, they can reconstruct changes in past ocean temperatures and, indirectly, patterns of salinity and ice volume. During intervals associated with amok slowdowns, including the Younger Dryas, certain deep-sea cores from the North Atlantic show signatures consistent with cooler surface waters and altered deep-water properties. The assemblages of foraminifera species themselves shift. Species that prefer warmer, well-mixed waters decline, while those more comfortable in colder or stratified conditions become more common. Mixed into those layers, you sometimes find coarser material, sand, pebbles, even bits of gravel. Too heavy to have drifted there by ordinary currents, they were transported by icebergs. As icebergs carve from glaciers and drift into the open ocean, they slowly melt and drop whatever debris they were carrying onto the seafloor. These pieces are called ice-rafted debris. An increase in ice-rafted debris at the onset of the Younger Dryas suggests that more icebergs were reaching the open North Atlantic, or that sea ice and cold surface waters were expanding into regions that had been relatively ice-free. Combined with the foraminifera and isotope evidence, the picture that emerges is of a North Atlantic surface that became fresher and colder, and of a deep ocean whose circulation pattern changed. Taken together, these clues have led many researchers to propose that the amok weakened sharply during the Younger Dryas. If less warm water was being carried northward and cooled there, then the North Atlantic atmosphere above would have received less heat. Winters would have intensified. Sea ice, once it expanded, would have reflected more sunlight and capped off evaporation, reinforcing the chill. Meanwhile, heat that would normally have been exported north might have lingered further south, perhaps contributing to the more modest or even opposite sign changes seen in parts of the southern hemisphere. To test whether these ideas can produce something like the observed records, climate scientists turn to models, mathematical representations of the atmosphere, ocean, ice sheets, and land surface, running on powerful computers. In these models, you can do experiments that are impossible in reality. You can pour a hypothetical pulse of fresh water into the North Atlantic and watch what happens. When models are forced with sizable freshwater inputs at high northern latitudes, many of them do produce a weakened amok. Temperatures in regions around the North Atlantic cool by several degrees. Sea ice expands, monsoon systems in the tropics shift. Some of the broad patterns resemble what the Proxy data suggest for the Younger Dryas: sharp cooling in Greenland and the North Atlantic sector, reorganization of rainfall in the tropics, and a more muted response in the far south. But models are not crystal balls. They are approximations with limits. Different models respond with different levels of sensitivity. Some require enormous freshwater pulses to trigger large AMOC changes. Others tip more easily. The exact timing of simulated cooling events and their duration depends on assumptions about the state of the ice sheets, the routing of meltwater, and the background climate. It is still challenging for models to reproduce, all at once, the full magnitude and abruptness of the Greenland cooling, the detailed structure of regional changes, and the precise 1,000-year length of the Younger Dryas. Moreover, while models can show that disturbing the AMOC can generate Younger Dryas-like patterns, they do not uniquely identify the real-world trigger. Freshwater could come from gradual ice sheet melt, from sudden lake drainages, or from more exotic mechanisms. Internal variability in the coupled ocean atmosphere system might also play a larger role than we currently realize. So the ocean story, compelling as it is, remains an interpretation, stitched together from microfossils, isotopes, stones dropped from ancient icebergs, and experiments inside supercomputers. Still, it offers a framework. The idea that the climate switch at the start of the Younger Dryas may have been thrown, at least in part, by changes in how the North Atlantic circulated heat. To see whether that framework holds, we have to follow the water more closely, trace the specific paths meltwater might have taken from the shrinking ice sheets of North America into the ocean, and ask whether those routes line up in space and time with the sudden return of the cold. To follow the water, we have to leave the open ocean and walk, very slowly, across a continent that no longer exists in the form it once had. At the end of the last ice age, North America was divided by ice. To the east, the Laurentide ice sheet, a slab of frozen water more than a kilometre thick in many places, sprawled from what is now the American Midwest up into Canada and toward Greenland. To the west, the Cordilleran ice sheet draped over the mountains of British Columbia and Alaska. Between and along the margins of these frozen walls, meltwater pooled. Wherever ice blocked natural drainage, water had only two options: find a low point, or wait. When it waited, it formed glacial lakes. The largest of these, or at least the most famous, was Lake Agassiz. It sat along the southern and western margin of the Laurentide ice sheet, covering parts of what are now Manitoba, Ontario, Saskatchewan, North Dakota and Minnesota. At its maximum, it may have held more freshwater than all the modern Great Lakes combined. And it was not alone. There were other proglacial giants: Lake Ojibwe farther east, lakes perched in Montana and Alberta, temporary inland seas dammed in front of retreating ice lobes. These lakes were not just pretty features on a map. They were climate-relevant reservoirs, enormous volumes of fresh water perched precariously at high latitudes, waiting for an outlet. As long as those outlets carried meltwater gently, through rivers that threaded into the interior of the continent, the influence on the ocean was probably gradual. But ice margins are restless. They thin, they retreat, they surge forward, they collapse. Each change can open or close a spillway, and when a new escape route cuts through an ice or sediment dam, the flow can shift from gentle to catastrophic. For the Younger Dryas story, the crucial question is simple to state and hard to answer. Where did these lakes drain, and when? One family of ideas points north and east. In this view, lakes like Agassiz and Ojibwe periodically spilled into the Arctic Ocean, or directly into the North Atlantic through routes along Hudson Bay, Hudson Strait, or the Labrador Sea. Cold, fresh water delivered there could have floated out over the salty subpolar North Atlantic, just where deep water likes to form. If enough of it arrived over a short enough time, it could have helped push the amok toward a weaker mode. Another set of possibilities points south and east, through what is now the interior of the United States. As the ice margin pulled back, meltwater and lake overflows may at times have been routed down the Mississippi system, ultimately reaching the Gulf of Mexico. From there, freshened surface waters could have been swept into the Atlantic via the Loop Current and the Gulf Stream. There are even scenarios in which drainage paths jumped back and forth over centuries, sometimes sending more water to the Arctic, sometimes to the Atlantic via the Gulf. As small changes in ice geometry and land surface elevation rearranged the plumbing of the continent. We don't have satellite footage of any of this. What we have is the landscape itself, and the quiet, stubborn marks that water leaves behind. If you stand today on the flat plains of central North America and squint at the horizon, you are looking at the floor of ancient lakes. Long, nearly level surfaces stretch for hundreds of kilometers, bounded by faint ridges or escarpments. Those ridges are former shorelines, the beaches of lakes that have been gone for more than 10,000 years. Follow those shorelines upslope, and you find staircases, multiple benches marking different lake levels as water rose and fell. Cut across them, and you encounter deltas of sand and gravel built where rivers once delivered sediment into standing water. Each delta, each strand line, records a pause in the tug-of-war between meltwater inflow, evaporation, and changing outlets. Where lakes found an escape, the signs are louder. Spillways carved by glacial outburst floods are oversized compared to the modest rivers that occupy them today. Their channels are broad and steep-walled, their floors littered with boulders too large to have been moved by normal flows. Bedrock surfaces are polished and grooved. Gravel bars pile up in patterns that match what we see in modern Jökull-lops, sudden floods that burst from beneath glaciers in Iceland and Greenland. In parts of Manitoba and Ontario, these abandoned spillways aim northward toward Hudson Bay. In others they swing south and east, linking to river systems that flow toward the Great Lakes and the Mississippi. Each one suggests a past drainage route. Each one has to be dated. Dating is where the story begins to blur. We can estimate when a lake stood at a particular level by dating the shells of freshwater organisms in its sediments, or by using cosmogenic nuclides, rare isotopes that build up in rocks exposed to cosmic rays, to time how long a former shoreline has been ice-free. We can constrain when a spillway last carried catastrophic flow by dating the sediments inside it, or the surfaces it cut. At the same time, we have the Greenland ice cores and marine sediment cores that tell us when the climate snapped into the Younger Dryas state. We know, within a few decades to a century or so, when temperatures in Greenland plunged, when dust levels changed, when snow accumulation shifted. The difficulty is stitching these timelines together without overpromising. Dating uncertainties in the terrestrial record can be on the order of hundreds of years, sometimes more. Different methods sometimes disagree. A spillway may have been used multiple times. A lake shoreline may have been reworked. Because of those uncertainties, there is still debate about whether specific outburst floods from Lake Agassiz or its siblings lined up exactly with the onset of the Younger Dryas, or whether they occurred slightly before or during, or even after the main cooling began. Some reconstructions suggest a large drainage eastward into the North Atlantic, roughly coincident with the start of the event. Others point to major rerouting toward the Arctic or Gulf of Mexico a bit earlier or later. Instead of a single cinematic flood flipping the climate like a switch, many researchers now picture a sequence of pulses. In this view, glacial lakes repeatedly adjusted their levels as ice retreated. Sometimes the water dribbled away through stable outlets. Sometimes an ice dam or moraine failed and released a surge. Each pulse delivered a finite volume of fresh water to the ocean. On its own, one might have nudged the amok, weakening it slightly before the system relaxed back toward its previous state. But if pulses came close together in time, into an ocean already near a threshold, they could have pushed it over. Climate models respond to this kind of staircase forcing in a staircase way. Add a burst of fresh water. The AMOC weakens. Let the forcing subside. The system stabilizes at a new, somewhat altered state. Add another burst. It steps down again. The result can be a pattern where climate variables, temperatures in Greenland, sea ice extent, rainfall belts, shift not as smooth curves but in jumps. When scientists look closely at some high-resolution records of the last deglaciation, they do see hints of step-like behaviour. Not just one clean break into the Younger Dryas, but a series of smaller wiggles and thresholds, as if the Earth system were feeling its way down a set of stairs rather than sliding down a ramp. It is tempting to assign each step to a particular flood, to match every notch in a shoreline to every kink in a temperature curve. But here caution is part of the discipline. Correlation in time is suggestive, not conclusive. The continent-scale plumbing was complex. Internal variability in the ocean and atmosphere could have amplified or muted the influence of any given meltwater pulse. So, when we speak of Lake Agassiz and its companions as possible triggers, it is best to imagine them as participants in a crowded room rather than as solitary actors on a stage. They were enormous reservoirs of climate-relevant fresh water. Yes. They almost certainly released that water in episodes, some of them dramatic. Their spillways and shorelines and flood deposits show that the continent endured moments of extreme hydrological reorganization. But the exact choreography, how those moments lined up with the beginning, middle and end of the Younger Dryas, remains an open puzzle. And into that uncertainty other ideas have flowed. Perhaps there were additional sources of fresh water. Perhaps the ice sheets themselves contributed in more complex ways. Or perhaps something more abrupt and unusual disturbed the climate system, with meltwater acting more as accomplice than mastermind. To explore those possibilities, we have to look beyond lakes and rivers and consider fires in the sky. When people hear fires in the sky, one idea arrives almost automatically. Something hit us. That is the core of what's called the Younger Dryas impact hypothesis. It doesn't claim that an asteroid ploughed into New York City or that a single giant crater lies waiting to be found. Instead, it suggests that somewhere around 12,800 years ago, Earth passed through a cloud of cometary debris or was struck by one or more fragments of a disintegrating comet. The impacts in this view did not need to be dinosaur killer scale. A swarm of smaller airbursts and surface explosions might have been enough. Enough for what? In the most ambitious versions, enough to set vast areas of the northern hemisphere on fire, to loft soot and dust and water vapour into the atmosphere, to darken skies, disturb climate, and perhaps help push the Atlantic circulation into a weaker mode. Some tellings fold in megafaunal extinctions and cultural disruptions among human populations as part of the same event. It is an arresting story. Cosmic impact, sudden cold, dying mammoths, and struggling hunter-gatherers all stitched into a single narrative thread. That narrative power is part of why the hypothesis caught attention, both in the scientific literature and far beyond it. But in science, attention is only the beginning. A hypothesis like this has to live or die on evidence. Impact researchers and sympathetic geologists pointed to several kinds of clues they argued were concentrated at the onset of the Younger Dryas, scattered across sites in North America, Europe, and the Middle East. One category is tiny, almost unimaginably so: microspherules. These are little glassy or metallic beads, usually less than 1 millimeter across, that can form when rock and soil are flash melted and then cool quickly while airborne. Large impacts and powerful airbursts can produce them. Advocates of the impact idea reported spikes in these microspherules in sediments they dated to around the Younger Dryas boundary. Another proposed marker is melt glass. Under a microscope, some grains in these layers look altered. their mineral structures twisted by extreme heat. Some samples show textures and compositions that have been argued to be consistent with rapid melting at temperatures that ordinary wildfires would struggle to reach, but that impacts might briefly create. Then there are nanodiamonds, crystals of carbon so small they have to be detected with specialized instruments. Certain types of nanodiamonds can form under high-pressure, high-temperature conditions associated with impacts. Reports of elevated nanodiamond concentrations in boundary layers gave the impact hypothesis another line of supposed support. Finally, a subtler signal: anomalies in the abundance of elements like platinum. In ice cores and some sediments, researchers have identified layers where platinum levels jump relative to background. Because some meteorites are rich in platinum group elements, such spikes can be interpreted as a hint of extraterrestrial input. Taken together, microspherules, melt glass, nanodiamonds, and platinum anomalies outline a kind of forensic kit for cosmic violence. If they all appear at the same time horizon over broad regions at concentrations well above background, and if independent labs can reproduce those findings, then the case for some sort of unusual event becomes stronger. This is where the story becomes more tangled. Many of the early studies reporting these markers came from teams that already favoured the impact interpretation. Other researchers, sceptical but curious, tried to replicate their work, same kinds of sediments, similar methods, but independently collected and analysed. Sometimes they found signals, sometimes they didn't. In some locations, microspherule spikes appeared near the Younger Dryas boundary. In others, counts were unremarkable. Some groups reported abundant nanodiamonds. Others, using different preparation techniques, reported almost none. Platinum anomalies appeared in certain ice core layers, but not always cleanly aligned with the onset of cooling in every record. Under the microscope, supposed impact melt glass in some samples looked, to other eyes, more like material that could have been produced by intense surface fires or by volcanic processes or by lightning strikes into sandy soils. In a complex dynamic landscape, there are many ways to generate heat. Dating added another layer of uncertainty. To argue for a global or hemispheric event, the relevant layers have to line up in time within, at most, a century or two. Yet radiocarbon dates, stratigraphic correlations, and local disturbances all introduce wiggle room. In some sequences, the proposed impact markers seem slightly older than the main cooling. In others, slightly younger. In still others, they were smeared across thicker intervals. None of this automatically disproves the idea that something from space happened, but it does weaken the case for a single, sharply timed catastrophe that neatly explains the Younger Dryas on its own. There is also a broader principle at work. The impact hypothesis is, in many ways, an extraordinary claim. It asks us to believe that a cluster of cosmic explosions not only occurred, but also triggered continent-scale wildfires, contributed to megafaunal extinctions, disrupted human cultures, and helped flip the climate into a 1,000-year cold spell. Extraordinary claims are not forbidden. They are simply asked to clear a higher bar. That bar includes reproducible measurements, clear stratigraphic relationships, and signals that show up consistently at multiple sites, analysed by multiple independent teams. So far, the picture is patchy. Some individual markers, especially certain platinum anomalies, are taken more seriously and have wider support. A modest extraterrestrial dusting, or a small impact depositing metal-rich material in polar ice, is not outlandish. Other claims, particularly those involving ubiquitous, impact-derived nanodiamonds or continent-wide, ultra-high-temperature melt glass, remain heavily disputed. Most researchers studying deglacial climate today are comfortable saying that the Earth's surface is sometimes struck by cosmic debris, and that such events can, in principle, influence climate. They are less comfortable tying the entire Younger Dryas episode to a specific impact scenario. A softer middle ground exists. Instead of a dramatic swarm of explosions igniting half a continent, perhaps a smaller impact, or a series of modest ones, perturbed the system in subtler ways. An object exploding over an ice sheet could, for example, melt or fracture ice locally, altering drainage pathways and contributing to meltwater pulses. Fine dust lofted into the stratosphere might cool the surface briefly, much like volcanic aerosols do, nudging an already unstable circulation pattern toward a different mode. If the climate system was already near a threshold because of changing insulation, retreating ice, and shifting ocean currents, even a relatively small external jolt might have mattered. Cosmic rays, the high-energy particles constantly striking the upper atmosphere, have also been proposed as a possible influence on clouds and climate. Variations in their intensity, perhaps tied to solar activity or passages through denser regions of interstellar space, could, in theory, alter the balance between sunlight reaching the surface and being reflected back to space. Evidence for such effects on the Younger Dryas, however, is far from conclusive, and remains in the realm of possibility rather than consensus. Where things stand now is somewhere between dismissal and confirmation. There is broad agreement that Earth has experienced impactful encounters with space debris, and that the late Pleistocene was no exception. There is also broad agreement that the onset of the Younger Dryas coincides with complex changes in freshwater routing, ocean circulation, and atmospheric patterns that do not require an impact to be set in motion. What is still contested is whether a specific cosmic event around 12,800 years ago played a significant role, whether as trigger, amplifier, or footnote. For now, the safest way to hold the impact hypothesis in mind is as one possible accent in a crowded score. Maybe there was a brief moment when the sky added its own percussion to the rhythm already being played by ice, ocean, and orbit. Maybe not. The rocks and ice are still being read. Meanwhile, other ideas offer their own explanations for sudden cold spells, the breath of volcanoes, the flicker of the sun, and the restless noise of the climate system itself. To follow those threads, we have to look not up, but down, into the deep places where magma rises and ash is born. When magma reaches the surface in the right way, the planet coughs. Not every eruption matters for climate. Many volcanoes mostly release lava, water vapor, and carbon dioxide. These can shape landscapes, but their climatic fingerprints are usually subtle and long-term. What really changes the temperature, at least for a while, is something finer and more fragile: sulfate aerosols in the upper atmosphere. Imagine an explosive eruption powerful enough to punch material all the way into the stratosphere, 10, 20, 30 kilometers above the surface. There, sulfur-bearing gases, mostly sulfur dioxide, meet oxidizing agents and sunlight. Over days to weeks, they transform into tiny droplets of sulfuric acid, each droplet so small it can stay aloft for months or years. These droplets do not care about national borders or mountain ranges. They spread along latitude bands, sometimes circling the globe. As they do, they scatter incoming sunlight back into space. Less light reaches the surface. Days become a little dimmer, skies a little whiter, and average temperatures, especially over continents, fall. We have seen this in recent history. When Tambora erupted in 1815, the following year in parts of Europe and North America became known as the year without a summer. Snow in June, frosts in August, harvest failures. After Pinatubo in 1991, global surface temperatures dipped by roughly 0.5 degrees Celsius for a couple of years. The planet's long-term warming trend did not reverse, but it paused, briefly masked by that veil of sulfate. This is the basic logic many researchers bring to ancient cold spells. If a single volcano can cool the globe for a year or two, what could a truly gigantic eruption do? Or, more intriguingly, what could a rapid sequence of big eruptions achieve? To answer that for the distant past, scientists turn again to ice. Greenland and Antarctica do not just trap bubbles of old air. They also quietly record volcanic breaths. When a large eruption injects sulfur into the stratosphere, some fraction of those sulfates eventually fall out, carried by precipitation, frozen into snow. Year after year, storm after storm, that snow is buried, compacted, and transformed into ice. Drill down through that ice, and you can, in places, read the history of volcanism almost year by year. Spikes in sulfate concentration mark moments when the sky was briefly clouded with volcanic aerosols. If multiple ice cores in different locations all show a sulfate peak at the same depth, it suggests a big, possibly global eruption. If only one or two show it, the eruption might have been more regional, affecting one hemisphere more than the other. When scientists look at ice from around 12,800 years ago, they do see sulfate layers. The late glacial period was not volcanically quiet. There are intervals with elevated sulfur, hints of sizable eruptions in the centuries before, during and after the Younger Dryas onset. The question is not whether volcanoes were erupting. They almost always are somewhere. The question is whether their activity lines up in timing and strength with the dramatic cooling. To use volcanism as a main explanation, you would ideally want a few things. You would want one or more very large sulfate peaks, right at, or very slightly before the onset of the Younger Dryas in multiple independently dated ice cores. You would want those peaks to be significantly larger than the background volcanic noise, and you would hope to identify corresponding ash layers, tiny glass shards from the same eruptions that could be traced back to specific volcanoes or regions. Pieces of this picture exist, but they are not yet neatly assembled. Some studies have reported notable sulfate spikes near the Younger Dryas boundary in Greenland cores. Others, using higher resolution measurements or updated chronologies, have adjusted the timing of those spikes, nudging them a bit earlier or later relative to the sharp cooling seen in oxygen isotopes. Antarctic records, which would capture large tropical eruptions affecting both hemispheres, do show big events around the broader deglacial period, but not all of them coincide cleanly with a Younger Dryas onset. Then there is the issue of duration. Volcanic sulfate aerosols in the stratosphere are surprisingly short-lived. They tend to fall out within about 1 to 3 years. Even very large eruptions, like those thought to be behind some prehistoric volcanic winters, are expected to produce strong cooling for a handful of years, fading over a decade or two as the aerosol veil thins. The Younger Dryas lasted roughly 1,000 years. To stretch volcanic cooling across that span, you have to imagine not just one eruption, but a cluster, a century or more in which powerful volcanoes erupt frequently enough that the atmosphere is repeatedly recharged with sulfate. In principle, a series of eruptions spaced every few years could keep average temperatures depressed, especially if the climate system was already tipped toward cold. This is where interaction with the oceans comes in. The atmosphere responds quickly to volcanic aerosols. The upper ocean responds more slowly. The deep ocean, slower still. If a sequence of eruptions briefly cools surface waters in key regions of the North Atlantic, it could, in some models, help alter density patterns and circulation strength. Cooler, fresher surface water is less likely to sink. If sinking weakens, so can the overturning circulation that carries heat northward. In that kind of scenario, volcanoes would not need to provide 1,000 years of direct cooling. They would only need to give the system a shove at the right moment, helping an already wobbling circulation pattern slip into a new, colder mode. Once the Atlantic overturning weakens, internal feedbacks, ice growth, changing winds, sea ice cover might sustain the new state long after the last aerosol droplet has fallen. Models exploring this sort of interplay do show that under some conditions, volcanic clusters can amplify or prolong existing cool trends. But the results depend heavily on starting assumptions. How sensitive the circulation is, how big the eruptions are, how quickly the ocean mixes heat. As with impacts, the standard for strong evidence is demanding. For volcanism to be considered a primary driver of the Younger Dryas, researchers would look for a few converging lines of proof. Clear, well-dated sulfate peaks in multiple ice cores right at the transition. Consistent signals in both hemispheres if the eruptions were tropical, or strong northern signals if they were high-latitude northern events. Distinct ash shards that can be geochemically matched to specific volcanic sources. And ideally, climate model simulations showing that eruptions of the inferred size and timing are capable of recreating the observed patterns of cooling, especially the sharp onset and the regional distribution of temperature changes. At present, the record is suggestive rather than definitive. There were eruptions. Some may have been large, some may have occurred close in time to the start of the Younger Dryas. Whether they were sparks, background noise, or something in between remains open. What most researchers can agree on is that volcanic forcing almost certainly contributed to the day-to-day and decade-to-decade variability of climate during deglaciation. Years of strange summers, of dimmer skies and poor harvests would have punctuated the broader trends in temperature and ice. Whether those breaths from the deep were enough to flip the whole system, or merely added texture to a story already being written by melting ice and shifting currents, is still under examination. To explore the other possibilities, we have to turn our attention from fire and sulfur to a quieter set of players. The slow wobble of Earth's orbit, the subtle moods of the sun, and the internal noise of a climate system that can surprise even without any obvious external shove. When people first hear about abrupt climate shifts, they often imagine some dramatic external switch being thrown. A comet, a supervolcano, a sudden shutdown of a current. Something big and obvious. But some researchers are drawn to quieter suspects. Gentle changes in sunlight, slow rearrangements of wind belts, patterns that emerge from the system itself without any single dramatic trigger. To understand how these might relate to the Younger Dryas, we have to step back and look at the bigger rhythms of the planet. Start with the sun. The sun is not a perfectly constant lamp. Its output wobbles a little, mostly on cycles of about 11 years as magnetic fields twist and relax. During active periods, sunspots and bright faculae slightly alter the total energy Earth receives. Over decades and centuries, these ups and downs can add a faint, flickering quality to climate. Today we measure that variability with satellites, instruments sensitive enough to detect changes of a fraction of a percent in solar energy. For the deep past, we have to rely on indirect clues. When the sun's activity changes, it also affects the rain of high-energy particles from space cosmic rays that reach the upper atmosphere. Those cosmic rays help create rare isotopes like beryllium-10 and carbon-14. Snow in Greenland, ice in Antarctica, tree rings in ancient forests, all of them silently record these isotopes. Higher concentrations can hint at quieter phases of solar activity, lower concentrations at more active phases. The records are noisy and require careful calibration, but they give us a way, however imperfect, to trace the sun's moods thousands of years back. When scientists examine beryllium-10 in ice cores across the Younger Dryas onset, they do see variations. There are hints of solar cycles, of periods when the sun may have been slightly more or slightly less active. But slightly is the key word. The magnitude of typical solar variability over decades appears small changes in total energy on the order of 0.1% or less. That is enough to leave a fingerprint on regional climates, to nudge storm tracks and monsoon patterns, especially when amplified by feedbacks like sea ice and snow. It may not on its own be enough to plunge the North Atlantic region back into full glacial chill. This is where internal variability comes in. The climate system is not a passive receiver of sunlight and volcanic dust. It is a restless, interacting network of oceans, atmosphere, ice, and land. Even if external conditions stayed perfectly constant, the system would still shift and slosh, much like water in a basin never really comes to rest. We see this today in phenomena with familiar names. El Niño and La Niña in the Pacific, for example, are born from internal feedbacks between trade winds, sea surface temperatures, and thermocline depth. The system flips every few years, making some winters wetter, some summers drier, without any change in the amount of sunlight reaching Earth. On longer timescales, there are patterns in the North Atlantic too, modes of oscillation in sea surface temperatures and atmospheric pressure that can persist for decades, sometimes called the Atlantic multi-decadal variability. There are also slow seesaws in the strength of the Atlantic overturning circulation, the great conveyor that carries warm surface water north and cold deep water south. During deglaciation, when ice sheets are shrinking and meltwater pulses are freshening the oceans, these internal patterns may have been especially sensitive. A slight change in winds, a modest shift in sea ice cover, a few consecutive years of unusual weather could, in principle, tip the balance between a vigorous overturning state and a sluggish one. This is the essence of threshold behaviour. Imagine the climate system as a landscape of hills and valleys. Under some boundary conditions, ice sheets of a certain size, greenhouse gas levels within a particular range. The system has two stable valleys it can rest in, a relatively warm one with strong ocean circulation and limited sea ice, and a colder one with weaker circulation and expanded winter ice. As long as the system sits deep in one valley, little nudges, small volcanic eruptions, modest solar dips, decade-scale wind anomalies will just jostle it around without moving it to the other side. But as conditions evolve, as ice sheets retreat and fresh water accumulates in key ocean basins, the ridge between the valleys may lower. The system approaches a threshold at that point. Even a small push can send it rolling into the neighbouring state. In this picture, you do not necessarily need a single towering trigger to explain something like the Younger Dryas. You might instead have a slow approach to a threshold as orbital cycles, greenhouse gas changes, and ice sheet melt all reshape the background. Then perhaps a combination of modest factors, a brief downturn in solar output, a cluster of mid-sized volcanic eruptions, a few decades of unfavourable wind patterns, combine to tip the scale. The challenge is seeing this in the data. Proxy records are powerful, but they are not omniscient. Ice cores from Greenland can be sampled at very high resolution, sometimes year by year for the late glacial period. They show abrupt shifts in oxygen isotopes that we interpret as temperature changes, along with dust, sodium, and those beryllium-10 traces of solar activity. But even in the best cores, there are limits. Diffusion in the firn, the compacting snow, smears the chemical signals over time. Small, rapid changes can be blurred together. Dating uncertainties, even if only a few decades, make it hard to say whether a particular solar minimum, a modest sulfate spike, and a shift in ocean proxies lined up exactly, or simply overlapped within a century. Marine sediments, which tell us about ocean temperatures, salinity and currents, usually have coarser resolution. A single layer might represent 50 or 100 years of deposition. You can see that the North Atlantic surface cooled rapidly around 12,800 years ago, and that deep water formation seems to have weakened, but teasing out 20-year steps in that transition is difficult. Speleothems, stalagmites and stalactites offer precise uranium-thorium dates and can record shifts in rainfall through oxygen isotopes. They show changes in monsoons and westerlies that seem to coincide with the Younger Dryas. Yet even here, interpreting the exact sequence of events at the scale of a human lifetime remains tricky. So, when scientists try to evaluate ideas about solar forcing, internal oscillations and threshold behaviour, they often run up against the same constraint. The records can tell us that the climate changed suddenly on human timescales, and that multiple parts of the system shifted together, but they struggle to resolve which small nudge came first. This has nudged thinking in a particular direction. Instead of hunting for a single, dramatic, smoking gun, Many researchers now entertain a more modest but perhaps more plausible scenario. In this view, the Younger Dryas is the product of several interacting influences, slowly changing orbital geometry that altered where and when sunlight fell, gradual retreat of ice sheets and the meltwater they released, modest but real variations in solar output, ordinary volcanic activity, and the internal dynamics of the oceans and atmosphere. None of these, by itself, may look impressive enough to explain a 1,000-year cold reversal. But operating together on a system already close to a threshold, they could have been sufficient. A slightly weaker sun might have helped expand winter sea ice in the North Atlantic. That extra sea ice could have reflected more sunlight, cooling the region further. Cooler, fresher surface waters might have become less likely to sink, weakening the overturning circulation. Changing winds could have reinforced this pattern, steering storms and meltwater in ways that maintain the new state. Once established feedbacks involving ice, snow and vegetation could have held the system in that colder mode for centuries until the slow march of orbital change and greenhouse gases nudged it back again. In this multi-cause picture, there is no single moment when everything changes because of one dramatic event. Instead, there is a period of increasing tension, a crossing of a threshold, and then a settling into a new equilibrium that feels, from the perspective of ice cores and sediment layers, very abrupt. For people living through it, it would have been both sudden and gradual. A few years of harsher winters, a decade of unreliable summers, rivers that froze longer, animals that shifted their ranges, plants that struggled to grow where they once had thrived. By the time anyone realized the old climate was gone, the new one would have felt normal to the children who had grown up in it. To see how that new normal reshaped the world on the ground, we have to leave the abstract language of proxies and thresholds and return to landscapes and lives. In the next part of the story, the Younger Dryas stops being a line on a graph and becomes a place, the ice-fringed plains and forests of Europe and Asia as they stiffened, stalled and waited for warmth to return. In Europe, the new climate did not arrive as a wall of ice sweeping south. It arrived as a return of habits the land had only just begun to forget. In the warm centuries before the Younger Dryas, glaciers in the Alps and Scandinavia had been shrinking. Valleys once filled with ice were opening into raw, unstable slopes. Thin soils were forming, streams were cutting new channels, and pioneering plants were creeping up the freshly exposed ground. Then, around 12,800 years ago, the trend reversed. In many mountain ranges, glaciers stabilized or pushed forward again, not to their towering maximums of the last glacial peak, but enough to reclaim ground they had ceded. Moraines that had been forming in retreat began to stack up in advance. Ice tongues fattened, crept down valleys, and in some places snapped off new blocks that tumbled and melted in the rivers below. Beyond the glaciers themselves, the near-glacial or periglacial world returned. Permafrost crept southward. Winter frost dug deeper into the soil. In many regions, the ground surface became a kind of restless skin, freezing, heaving, cracking, then thawing just enough in summer to slump. Stones slowly migrated into patterned circles and stripes. Shallow ponds appeared and vanished with the seasons. Hillsides flowed in slow motion as ice within the ground expanded and shrank. For people, this meant the land itself felt less reliable. Trails might be fine one year and boggy or unstable the next. Slopes that had been safe to cross could suddenly fail. Campsites with good drainage turned into quagmires after a few seasons of freeze-thaw. Vegetation shifted with the cold before the Younger Dryas. Mixed forests had been spreading north in Europe. Birch and pine first, then hazel, oak, and other broadleaf trees, following the warming weather. The dark green line of woodland was steadily advancing toward the retreating ice. Under the Younger Dryas chill that advance stalled. In many places it reversed. The northern and high-altitude edges of the forest belt thinned out, and broke apart. Trees became scattered, stunted, clinging to sheltered hollows. In their place spread a familiar but harsh environment, steppe tundra. Think of a mosaic of low shrubs, grasses, sedges and hardy herbs, broken by patches of bare soil and gravel. Winters long and dry, with snow scoured away by wind. Summers short and bright, but cool, with plants rushing through their annual cycle in a few frantic weeks of thaw. This steppe tundra was not uniform. In some corridors along rivers, in sheltered basins, patches of woodland held on like islands in a cold sea. But over much of northern Europe and western Asia, the broad trend was clear. Forests retreated south and downslope. Open, treeless landscapes reclaimed the margins. Rainfall patterns shifted too. The great westerly winds that carry Atlantic moisture into Europe did not stop, but their paths and strength changed. In some regions, winters became snowier. In others, both winter and summer grew drier. The balance between rain and snow altered the way water moved across the land. Rivers responded. Some channels that had been wide and braided under strong meltwater flow began to shrink, cutting deeper into their beds as discharge decreased. Others, fed by renewed glacial melt in certain mountain areas, became more seasonally extreme, roaring with icy floodwater in late spring, then dropping to low cold trickles by the end of summer. Floodplains changed shape. Places that had been reliable fishing spots or easy crossing points might become cutbanks and marshes. Oxbow lakes formed as meanders were abandoned. Fine sediments, silts and clays were reworked and redeposited, sometimes covering old campsites, sometimes stripping them away. Soils were caught in the same reshuffling. Under steppe tundra with short growing seasons and frequent freezing, soil development slowed. Organic matter broke down more slowly, and winds could more easily strip away exposed fine particles. In some areas, loess, dusty, wind-blown silt, accumulated again, blanketing the land in pale, fertile, but initially unstable layers. In others, thin soils eroded, exposing gravel and bedrock. These changes mattered because people had organized their lives around specific seasonal resources. Salmon runs in certain rivers, herds that migrated along familiar routes, nut groves that ripened in a predictable month, marsh plants that could be dug at a known time. When forests retreated, some of those resources vanished or shifted. Hazelnut stands that had provided concentrated bursts of calories in late summer might have withered or moved south. Browsing animals that depended on woodland undergrowth had to adjust their ranges or decline, while grazing animals more suited to open steppe, like reindeer and wild horses, may have found new opportunities, at least in certain regions. Around the Mediterranean and the Near East, the story was more nuanced. This was not a simple mirror of the far north. Ice sheets never advanced to the shores of the Aegean or the Levant. Olives, oaks, and pistachios did not suddenly give way to polar desert. But the Younger Dryas still left its mark. Many climate proxies from this region, lake levels, pollen, cave deposits, suggest a general tendency toward cooler and, in many places, drier conditions. Some lakes shrank, leaving behind rings of stranded shorelines. Wetlands contracted. In certain basins, wind-blown dust layers point to reduced vegetation cover and increased aridity. Yet the pattern was not uniform. Some areas, especially those influenced by shifting storm tracks and local topography, may have remained relatively moist or even seen increased winter rainfall. Coastal zones might have buffered temperature drops. High mountains could experience more snow even as lowlands dried. For early cultivators in the Near East, who were experimenting with wild cereals and managing stands of useful plants, these variations would have been critical. A slight shortening of the growing season, a few consecutive years of unreliable rains, could turn marginal fields into bad bets. People may have responded by moving to better watered microregions, shifting their plant focus, or leaning more heavily on hunting and gathering again. Archaeological sites in Europe and Western Asia often capture this period as a series of subtle breaks rather than a single dramatic collapse. In some caves and open-air sites, layers from the onset of the Younger Dryas show changes in stone tool styles, in the proportions of animal bones, in the presence or absence of hearths and structures. Reindeer bones, for example, might become more common in northern Europe as steppe tundra expanded. In parts of the Near East, gazelle hunting may intensify when plant resources faltered. But the relationship between climate and culture is not one-to-one. A layer showing fewer hearths does not necessarily mean famine. A shift in tool types does not automatically signal desperation. People innovate for many reasons: social fashions, new ideas spreading through networks, changes in trade relationships. Climate stress may be part of the backdrop, but it is rarely the only actor on stage. In some regions, archaeological sequences across the Younger Dryas look surprisingly continuous. Sites are occupied before, during and after the cold phase with no obvious break. Tool traditions evolve, but they do not shatter. This suggests that for certain groups the climate shift, while real, was something they could adapt to without abandoning their ways of life. In others, there are gaps, hiatuses in occupation, abrupt changes in settlement patterns, new kinds of sites appearing where none existed before. These may reflect local crises, rivers that shifted course, pastures that degraded, wood sources that became too scarce. Put together, the picture across Europe and Asia is one of landscapes pulled back toward glacial habits, but with regional accents and local improvisations. Glaciers inch forward in some valleys, permafrost reclaims certain plains, forests pause or retreat, steppe tundra spreads its pale, wind-brushed carpet once more. Rain belts wander, rivers reorganize, soils thin or pile up. On the ground, families and bands respond not just by suffering, but by adjusting routes, altering seasonal rounds, exploring new niches, clinging to favoured refuges where the old patterns still roughly hold. The Younger Dryas, in this view, is less an instant disaster than 1,000 local stories of adjustment written into ice, dust, pollen, and into the archaeological traces of people learning, again, how to live on a restless planet. To see how dramatic those adjustments could be when the cold struck a continent already in flux, we have to cross the Atlantic, to a land of melting ice sheets, giant lakes, and a sudden return of winter, North America in the Younger Dryas. North America met the Younger Dryas in the middle of a transformation that was already extreme. At the height of the last glacial maximum, roughly 20,000 years ago, two enormous ice bodies had dominated the continent: the Laurentide ice sheet over eastern and central Canada, and the Cordilleran ice sheet draped over the mountains of the west. Between and around them, tongues of ice had reached well into what is now the northern United States. By 13,000 years ago, those giants were in full retreat. Lobes of ice had pulled back from the Great Lakes region. Vast proglacial lakes, water trapped against the receding ice, had formed in front of the Laurentide margin. In the west, ice in many mountain valleys had thinned or vanished. Inland basins filled with meltwater and seasonal rivers that had not flowed in tens of thousands of years were re-establishing themselves. Then the Younger Dryas arrived, and the retreat slowed, paused, or in some places reversed. In eastern North America, the signal is clearest along the old ice front. Geomorphologists see a series of moraines, ridges of debris pushed up by the ice, marking still stands and minor redvances of the Laurentide margin that line up in time with the Younger Dryas. Glaciers that had been shrinking stabilized. Some thickened at their fronts, pushing forward small distances and dumping fresh loads of rock and sediment. They did not surge back to cover the Midwest, but they did reassert themselves as active cold engines at the northern edge of the continent. the air over much of the east cooled. Pollen records from lakes and bogs track the vegetation response. Before the Younger Dryas, as the planet warmed, deciduous trees, oaks, maples, elms had been marching north behind the retreating ice. Boreal species like spruce and pine had already claimed broad belts of land. The forests were layered, diverse, and steadily expanding. With the Younger Dryas, that expansion faltered. In many cores, the proportion of spruce pollen increases again, while more warmth-demanding trees retreat. Mixed forests give way temporarily to more boreal, conifer-dominated stands. In certain regions, particularly closer to the ice front, open parklands and even tundra-like communities re-emerge. Low shrubs, sedges, hardy herbs, with trees thinned or absent. Charcoal in those same sediments suggests that fire regimes shifted too. Under cooler, often moister conditions, some areas may have seen fewer large wildfires. In others, changes in seasonal dryness and vegetation structure produced different fire patterns rather than simply more or less burning. These subtleties matter because fire helped shape the mosaic of habitats that animals and people relied on. Further west, the story was not just about cold, it was about water or the lack of it. Many records from the interior west of North America, lake levels, shoreline deposits, cave formations, indicate that the Younger Dryas there had a strong drought component. Lakes that had been high under earlier deglacial conditions began to fall. Some split into smaller basins, others retreated toward their deepest parts, leaving broad, salty flats. Pollen from western basins points to vegetation adapted to drier conditions, more sagebrush and other desert or steppe species, fewer indicators of lush, closed woodlands. In higher elevations, montane forests may have cooled, but in adjacent valleys, the combination of less effective moisture and cooler temperatures could create surprisingly parched landscapes. This pattern cool east, dry and cool west, dynamic ice margin in between, set the stage for one of the most dramatic aspects of North America's Younger Dryas, the behavior of its glacial lakes. As the Laurentide ice sheet shrank, it repeatedly dammed and redirected enormous volumes of meltwater. Proglacial lakes, like Lake Agassiz in the center of the continent, Lake Ojibwe to the east, and a shifting set of lakes in the Great Lakes Basin waxed and waned as ice lobes moved and outlets opened or closed. During the Younger Dryas, these lakes did not sit quietly. Shoreline evidence and sediment cores show rapid changes in water level, sudden shifts in drainage routes, and episodes of massive outflow. In some reconstructions, Lake Agassiz and its siblings periodically spilled south into the Mississippi system. At other times, they found eastern or northern escape paths. In a few cases, they may have routed great pulses of freshwater toward the North Atlantic or the Arctic changes that some researchers link to the very onset of the Younger Dryas itself. Even without resolving every debate about exact paths and timing, the local impact is clear. When a glacial lake drops tens of meters as an outlet opens, it does not do so gently. Shorelines step down. River channels are carved and abandoned. Vast tracts of former lake bed are suddenly exposed, raw, silty plains, initially unstable, then slowly colonized by plants. If a dam of ice or sediment fails catastrophically, the result is a flood on a scale that dwarf modern river floods, a wall of water and debris scouring downstream valleys. Across the continent, these events created and erased wetlands, fisheries, and crossing points. A familiar bay where people had launched boats for generations might become a meadow within a human lifetime. A flat, dry corridor might be transformed into a marshy delta complex, rich in birds and plants, but difficult to traverse. All of this played out against a backdrop of moving coastlines. Sea level during the Younger Dryas was still significantly lower than today. Much of the continental shelf lay exposed as broad coastal plains. The coastlines of eastern North America, the Gulf of Mexico, and the Pacific Northwest lay farther out. Estuaries, lagoons, and river mouths occupied different positions. As deglaciation continued, even with the Younger Dryas pause, meltwater kept entering the oceans. Shorelines crept landward over centuries. In some areas, especially where isostatic rebound, the slow uplift of land previously weighed down by ice was strong. The relative sea level story was more complex, with local coasts rising even as global seas rose. For any humans living along those margins, resource zones were shifting. Shellfish beds, kelp forests, and tidal flats moved with the shoreline. Low-lying campsites could be drowned over generations. But much of this movement was on timescales long compared to a single life, more like a slow background drift than an immediate catastrophe. Migration corridors, both terrestrial and coastal, were also being reshaped. In the interior, as the Cordilleran and Laurentide ice sheets pulled apart, an ice-free corridor had opened and closed in different forms over time. The Younger Dryas intersects with one of those phases when parts of this corridor contained lakes, wetlands and steppe-like habitats, rather than a single clear, dry highway. In the west, the drier Younger Dryas conditions may have put stress on some interior routes, while making others more predictable, favouring particular river valleys or springs. Along the Pacific coast, lowered sea levels still offered the possibility of a kelp highway, a string of productive nearshore environments that could support marine-oriented groups even as glaciers retreated from fjords and inlets. From the perspective of people on the ground, North America during the Younger Dryas was not a uniform ice world. It was a patchwork. Cooler boreal forests and pockets of tundra in the east, drying basins and shrinking lakes in parts of the west, active ice margins and restless glacial lakes near the great northern ice sheets, coastlines edging landward, opening and closing inlets, reworking estuaries. Archaeologists find human presence threaded through this changing landscape. Stone tools and camp debris on old lake terraces, sites on river bluffs that overlook former floodplains, traces on what were once inland dunes or steppe. It is tempting to draw a straight line from every climatic shift to a human response. Drought triggers migration, cooling forces technological innovation, a glacial flood destroys a settlement. Sometimes those links may be close. A sudden lake drainage could indeed wipe out local wetlands that sustained a group. A shift from forest to open steppe might favour hunters specialised in particular prey. But, as with Europe and Asia, correlation is not the same as causation. People move, change tools, and alter their subsistence for many reasons. Social alliances, conflict, curiosity, the pull of new marriage networks, the allure of raw materials or rich hunting grounds heard about from distant contacts. Climate and landscape change set the stage. They alter which options exist, which routes are possible, which resources can be relied on. But they do not by themselves write the script of human history. In North America during the Younger Dryas, that script includes something else as well. The fate of the continent's great animals, the mammoths, mastodons, giant ground sloths, and other megafauna that had survived previous glacial swings but would not make it far into the new, warmer epoch that followed. To see how this climatic pause, with its cold east, dry west, restless lakes, and shifting coasts intersected with those disappearances, we turn next to the story of megafauna, extinctions, and a changing world. When people talk about the end of the Ice Age, they often picture it in terms of animals first. Not pollen diagrams, not ice cores, but mammoths on windy plains, saber-toothed cats watching from ridges, giant ground sloths lumbering through strange open woodlands, herds of horses, camels and bisons stretching to the horizon. In the late Pleistocene, that picture was real. Across North America, Eurasia, and parts of South America and Australia, ecosystems were built around very large animals, megafauna, usually defined as species over about 45 kilograms, or roughly the size of a big dog and up. These weren't just oversized curiosities, they were ecological engineers. Mammoths and mastodons pushed over trees and open clearings. Giant herbivores trampled and fertilized soils. Big predators shaped the behavior and movement of everything smaller than they were. By the time the Younger Dryas began, many of these animals were still there. In North America, you would have found mammoths and mastodons, giant ground sloths, ancient bison, North American horses, camels, short-faced bears, American lions, dire wolves, saber-toothed cats, and more. In Europe and Northern Asia, woolly mammoths, woolly rhinos, steppe bison, giant deer with antlers like living trees. In South America, an array of strange ground sloths, armoured glyptodonts and litoptons and notungulates, hooved animals unlike anything alive today. The crucial question is timing. When did they disappear? And how does that line up with climate swings like the Younger Dryas, and with the arrival and spread of humans? Here the story becomes both fascinating and frustrating. Radiocarbon dates on bones, dung, and associated materials give us broad windows. In North America, many megafaunal populations appear to have been healthy, or at least present through the Bulling-Olerode warm phase that preceded the Younger Dryas. Then, between about 13,000 and 11,000 years ago, many of them vanish from the record. Those numbers sound precise. They are not. Every radiocarbon date has an error range, sometimes a couple of hundred years, sometimes more. Dates must be calibrated to account for changes in atmospheric carbon over time, which introduces its own wiggles. Bones may lie around for decades or centuries before finally being buried and preserved. What this means in practice is that extinction chronologies can tell us that a species probably disappeared within a certain broad interval, often spanning many centuries. They can rarely say, with confidence, it died out exactly 530 years after this climate event, or within one human lifetime of that technological change. For North American megafauna, the main outline is this. Most of the large mammals that define the Ice Age ecosystems decline and disappear sometime between roughly 13,000 and 10,000 or 9,500 years ago. That window overlaps with the Younger Dryas, but it also stretches before and after it. Some species seem to linger regionally into the early Holocene. Others may fade earlier in particular areas while hanging on in refuges we have not yet sampled. So how does the Younger Dryas fit into this? One way to think about it is as a stress multiplier in a world that was already changing very fast. As the great ice sheets retreated, habitats were restructuring even without any extra cold snap. Grass-dominated steppe tundra, the favoured landscape for mammoths and some other grazers, fragmented and retreated north or broke into isolated patches. Forests advanced in some regions, wetlands expanded in others, dry steppe or shrubland grew in yet others. For a highly mobile, wide-ranging herbivore, this isn't instantly fatal. But it does mean that the old, continuous highways of suitable habitat broad, belts of cold, open grass and herb, became more like islands in an archipelago. Moving between them got riskier. Seasonal migrations had to adjust. Carving grounds that had worked for generations might no longer be reachable or safe. Add the Younger Dryas to that backdrop, and the picture gets even more complex. In some places, cooler, more open conditions may actually have given temporary respite to certain cold-adapted species, slowing their decline. In others, especially where dryness intensified, water sources became less reliable. Vegetation changed in structure, and the energetic costs of finding enough food and water may have gone up at the same time. Layer onto all this the spread of humans. By the onset of the Younger Dryas, people were present across large parts of Eurasia and the Americas. In North America in particular, some archaeological complexes, like the well-known Clovis tradition, are associated with large, fluted spear points that appear well suited to hunting big game. Kill sites where mammoths or other large animals show butchery marks and association with human tools demonstrate that people did sometimes hunt and process megafauna directly. But again, timing and scale are hard to pin down. There are not enough clear kill sites to suggest that every megafaunal death involved humans. Many species decline in regions where direct evidence of hunting is sparse. At the same time, even moderate levels of human predation, focused on key age or sex classes in a population, say a preference for prime-aged adults, can, in models, push already stressed populations into long-term decline. Climate stress, habitat change, and human hunting are often presented as rival explanations, each with its own camp. In reality, they are easier to see as interacting pressures. Climate change reshapes landscapes. Landscapes define the distribution and quality of habitat. Habitat change alters the vulnerability of animals to both natural mortality and human hunting. A species living at the edge of its climatic comfort zone in shrinking or fragmenting habitat may tolerate some predation or disturbance. That same level of predation applied when food is scarcer, seasonal refuges are gone, or migration paths are blocked, might tip the balance from persistence into slow collapse. This interacting pressures model is attractive because it can account for several observed patterns. It helps explain why extinctions cluster near times of rapid environmental change, like the end of the last glacial period, but do not always align exactly with single sharp events like the onset of the Younger Dryas. It allows for regional variation. In some areas, megafauna might decline mainly under climatic and vegetational shifts, with limited human influence. In others, intense hunting in key corridors could have played a larger role. It also highlights the limits of extinction chronologies. We can often say that a species last appears in a region around, for example 12,500 years ago, and that around the same general time, climate proxies show a shift, and archaeological evidence for people increases. But whether those curves are linked in a simple cause and effect chain, or in a more tangled web of feedbacks, remains open to interpretation. Single call stories are tempting for a reason. They are easy to remember and emotionally satisfying. Humans arrived and killed everything. Climate warmed and the Ice Age giants vanished. Each offers a clear villain or a clear mechanism, a neat moral or cautionary tale. Yet the more evidence accumulates from radiocarbon dates, from ancient DNA, from pollen and charcoal records, from increasingly detailed climate reconstructions, the more the late Pleistocene turnover looks like a systemic shift rather than a single blow. A world built around mammoths and other megafauna was giving way to a different world. Denser forests in many regions, smaller and more diverse herbivore communities, predator guilds with fewer truly giant members. The Younger Dryas was one sharp episode within that broader transition, a time when cold, drought and unstable waterscapes may have intensified the strain on already vulnerable species. By the early Holocene, when the Younger Dryas ended and climates in many regions warmed and stabilized, the new pattern was set. Many of the giant mammals were gone. Those that remained, like bison in North America, occupied changed ranges and lived alongside humans who were now embedded in these evolving ecosystems, not just as one predator among many, but as a force increasingly capable of reshaping landscapes themselves. To understand how people navigated that new world, with its altered animal communities and emerging opportunities and risks, we have to look more closely at the human side of this story, how our species lived at the very edge of the Holocene, in the aftermath of the last great age of ice and giants. When we zoom in on that edge of Holocene world, one region keeps coming up again and again in the evidence. The Near East, the lands around the eastern Mediterranean, from the Levantine coast across into the interior, hills and valleys where wild cereals grew, where gazelle herds moved with the seasons, where oak and pistachio woodlands thickened and thinned as the climate swung back and forth. Here, During and just after the Younger Dryas, we see people doing something quietly revolutionary. Archaeologists call some of them the Natufians. They were not farmers in the full textbook sense. They did not have domesticated wheat and barley in neat, ploughed fields. But they were also no longer just classic Pleistocene foragers, endlessly mobile, following herds across vast distances. They were something in between, in the Bulling Olerode warm phase before the Younger Dryas. Natufian groups in parts of the Levant began to settle more firmly. We find stone-built houses clustered in small villages, mortars and pestles for grinding plant foods, cemeteries where generations of people were buried in the same place. That kind of investment in a particular landscape implies expectation. You don't build permanent stone structures if you think you might have to abandon them next year and never return. The environment seemed to cooperate, at least for a while. Warmer, wetter conditions allowed stands of wild cereals, barley, emmer, einkorn, to spread on hillsides and valley floors. For a skilled forager, those were like natural grain fields, returning harvests year after year. Then the Younger Dryas arrived, and the pattern broke. Pollen records and lake sediments from the region suggest cooler, often drier conditions in many areas. In some places, steppe vegetation expanded at the expense of woodland. Water sources became more seasonal. The productivity of those wild cereal stands likely became more variable, more patchy. If you were living in a stone house in a Natufian village, that mattered. The response, as far as we can see from the archaeological record, was not a simple collapse back into wandering. It was more complicated and more interesting. Mobility patterns changed. Some sites that had been large and permanent seemed to shrink. Others are abandoned. New, smaller sites appear in different zones, sometimes in more favourable microclimates, near reliable springs or at elevations where moisture was more predictable. People seem to have dialed mobility up and down, not as a binary choice, but as a flexible strategy. They could maintain a base in a known place where burials and houses anchored social memory while sending out task groups to exploit scattered resources or shifting the centre of gravity of their lives when conditions forced it. Storage became even more important. Grinding stones become more common and more varied. Deeply worn mortars suggest repeated, intensive processing of seeds and grains. At some sites there are pits that may have been used to store food, cereals, nuts, dried meat, keeping surplus from good seasons to buffer the bad. Storage is a technical trick, but it is also a social one. Once you can store, questions follow. Who controls the stored food? Who guards it? Who decides when to open the pit? How to distribute the contents? Those decisions can create new social roles, new tensions, new forms of cooperation or inequality. We also see shifts in toolkits and subsistence. Stone tools become more specialized. Tiny backed blades and microliths, small standardized pieces appear in large numbers, well suited for composite tools like sickles or fine-tuned hunting weapons. Some of these sickle blades carry a distinctive sheen, polish formed by repeatedly cutting grasses and cereal stalks. Plant remains from sites show increased use of particular wild species, cereals, legumes, nuts, over time, and not in a perfectly smooth line. Some of those plants begin to show signs of human management. Seeds slightly larger, spikelets that shatter less easily, making them more convenient to harvest but less efficient at wild dispersal. Those are the early genetic fingerprints of domestication, though in the Younger Dryas itself, the process is only just beginning. On the animal side, hunting patterns change too. In some areas, gazelle remain a staple, but there is evidence of increased pressure on herds, more young animals in the kill profiles, suggesting hunting across a broader age range as populations become stressed. In other places, people broaden their diet, taking more small game, birds, fish, and even snails. This diversification looks like a classic human response to environmental uncertainty. Don't rely on a single mainstay if its abundance is becoming unreliable. Spread the risk across many species, many habitats, many seasons. All of this sits against the backdrop of climate that is not simply bad but unstable. Cooler and drier phases make some valleys harder to farm in the future. But they also create opportunities. Clearer ground may favour wild cereals in certain zones. Changes in gazelle migration routes might briefly concentrate herds in predictable choke points. Depressed lake levels can expose fertile floodplains. Climate, in this view, is not just a hammer of hardship. It is also a sculptor of opportunity. The Younger Dryas may have closed off some easy options that Natufian groups had relied on during the preceding warm phase. In doing so, it may have nudged people toward new experiments, tending patches of wild grain, weeding or protecting particularly productive stands, storing more food, returning deliberately to the same groves of nut trees or to favoured hunting blinds. Whether we call these activities proto-farming or simply intensified foraging is partly a matter of definition. But they point in the same general direction, a tighter, more managed relationship with particular plants and places. By the time the Younger Dryas ended around 11,700 years ago, and the early Holocene climate settled into a warmer, often wetter regime, those experiments were already in play. In some models, the sudden improvement in conditions is seen as the trigger. The climate stabilizes, wild cereals flourish, people seize the moment, and domestication accelerates. In others, the stress of the Younger Dryas itself is cast as the main driver. Only under pressure, when wild resources became less predictable, did people invest enough in controlling them to cross the threshold into true agriculture. The evidence does not clearly choose between these narratives. Radiocarbon dates on early domestic cereals and on Natufian and post-Natufian sites have uncertainties. The transition from collecting wild grain with slightly managed stands to cultivating truly domesticated crops is gradual, not a single leap we can easily pin to one climatic shift. Some regions of the Near East show earlier plant domestication than others, even under broadly similar climate histories. Social factors, existing settlement patterns, local traditions of storage and sharing, particular kinship systems likely shaped who adopted early cultivation quickly and who did not. What most researchers would agree on is that the Natufian to early farming transition unfolded within a tapestry where climate change, resource uncertainty, and human cultural innovation were tightly interwoven. The Younger Dryas did not, on its own, invent agriculture. But it seems to have been one of the last great tests of the Pleistocene way of life in the Near East, a period when people stretched the old foraging toolkit to its limits and began, perhaps reluctantly at first, to assemble a new one. When the world warmed again and the Holocene truly began, those new tools, storage, semi-sedentary villages, plant tending, social systems that could manage surplus, were ready to be scaled up. The Ice Age was over. The age of farmers, villages, and eventually cities was about to begin, built on foundations laid by people who had learned to live with uncertainty at the very edge of the Holocene. Then, almost as abruptly as it had arrived, the Younger Dryas was gone. From the point of view of a single lifetime, nothing about climate ever feels instantaneous. Winters and summers blur together, a few bad years of drought, a few good harvests, a particularly long winter. It's only when we step back and look at the records carved into ice, mud, and fossil shells that the drama really appears. In the Greenland ice cores, the Younger Dryas looks like a cliff. For more than 1,000 years, the isotopes that track temperature hover in a cold, glacial-like range. Then, over what appears to be just a few decades, perhaps even less in some interpretations, the signal shoots upward. Temperatures in the North Atlantic region jump by something like 5 to 10 degrees Celsius in a geological instant. This upshift marks the beginning of the Holocene, the warm, relatively stable interval we are still living in today. It is as if a switch in the climate system was flipped back the other way. In northern Europe, pollen records show forests racing poleward. Within a few centuries, cold-tolerant steppe and tundra plants give way to birch and pine, then to mixed deciduous woodlands. Lakes that had been partly frozen for long stretches of the year remain open water. Glaciers in the Scandinavian mountains begin a steady, long-term retreat. In the North Atlantic itself, tiny shells of plankton preserved in seafloor mud record a similar story. Species that prefer cold, ice-laden waters decline. Warm water forms move in. The chemistry of the shells shifts as surface temperatures and salinity change. But the speed of recovery was not the same everywhere. In some parts of the Northern Hemisphere, especially around the North Atlantic, the transition really does look like a snap, a swift step from one mode of climate to another. Elsewhere, the shift into the early Holocene appears more drawn out, more gradual. In the tropics, for example, many lake sediments and speleothems, mineral deposits in caves, suggest that changes in rainfall patterns took longer to settle. Monsoon systems strengthened, but not always in a single jump. The march toward a greener Sahara, with lakes and grasslands spreading across what is now desert, unfolded over centuries to millennia. In the southern hemisphere, the picture can be slightly offset in time. Antarctic ice cores show their own set of rapid changes, but not always perfectly synchronized with Greenland. There are leads and lags, hints that different parts of the climate system responded on different schedules as the world warmed. Taken together, these proxy records, ice, pollen, shells, cave minerals, tell us that the end of the Younger Dryas was both globally significant and regionally complex. A major reorganization of the climate occurred, but the way that reorganization played out depended on where you were standing on the planet. What could flip the system so fast? One leading explanation focuses on the same part of the climate machinery that may have helped trigger the Younger Dryas in the first place: the oceans. In many reconstructions, the cold phase is linked to a slowdown or re-rating of the Atlantic meridional overturning circulation, the great conveyor that carries warm surface water northward and returns cold, deep water southward. This circulation is sensitive to freshwater. Too much low salinity meltwater in the North Atlantic, and the dense, sinking limb of the conveyor can weaken. At the end of the Younger Dryas, the evidence suggests that this circulation strengthened again. Marine cores show shifts in the chemistry of deep waters, consistent with renewed formation of dense, sinking water in the North Atlantic. The distribution of certain microscopic organisms on the seafloor changes in ways that match a more vigorous overturning. Some models indicate that once ice sheet meltwater flux dropped below a threshold, the circulation could have recovered relatively quickly, pulling the climate with it. In that view, the termination of the Younger Dryas is another example of a threshold crossed. Meltwater input declines as the big northern hemisphere ice sheets adjust, the conveyor belt restarts, and warm Atlantic water once again pours northward, releasing heat to the atmosphere and rearranging storm tracks. The ice did not vanish overnight, but after the Younger Dryas, its retreat picks up speed. Sea level records from corals and coastal sediments show that global sea level continued to rise as the early Holocene unfolded, sometimes in pulses that may correspond to particularly rapid episodes of ice loss. In North America, the remnants of the Laurentide ice sheet retreat northward, leaving behind the Great Lakes and a patchwork of proglacial lakes that burst and drain as ice dams fail. In Europe, alpine glaciers pull back up valley. In Greenland, the ice margin shifts inland, exposing new land along the coasts. These changes feed into regional climates. Dark land and water surfaces absorb more sunlight than bright ice, amplifying local warming. For people living through this transition, the world would have felt increasingly open. Coastlines moved inland, sometimes flooding low-lying plains that had once been hunting grounds. River systems adjusted as glacial meltwater dwindled, carving new channels, abandoning old ones. Vegetation belts marched north or upslope, bringing new plant and animal communities into regions that had been sparse or barren. The new normal of the Holocene was not completely flat and calm. There were still variations, droughts, cold snaps, multi-century swings, like the so-called 8.2 kiloyear event. But compared to the wild swings of the late Pleistocene, the overall climate settled into a narrower band of variability. It is within that relatively stable band that agriculture spread, cities rose, and written history unfolded. The Younger Dryas, with its abrupt onset and abrupt end, has become one of the key case studies for how quickly the climate system can move between different states. For scientists thinking about modern climate risks, it is both a warning and a laboratory. The warning comes from the speed. The Greenland records in particular suggest that regional temperatures and circulation patterns can reorganize in a matter of decades, perhaps faster, once certain thresholds are crossed. That challenges any comforting idea that all significant climate changes must always be slow, giving societies centuries to adapt. The laboratory aspect lies in the details. By studying the Younger Dryas, researchers can test models of ocean circulation, ice sheet dynamics, and atmospheric feedbacks against something that actually happened. They can ask, under what conditions does the Atlantic conveyor weaken? How much fresh water is needed? How quickly does it recover? How do rainfall patterns shift when it does? No one expects an exact replay of the Younger Dryas in a world being warmed primarily by greenhouse gases rather than by orbital changes in deglacial meltwater. The boundary conditions are different, the ice sheets are smaller, the sources of forcing are not the same. But the principle that the climate system has multiple modes and that transitions between them can be sharp remains. The end of the Younger Dryas is a reminder that stability is not guaranteed, and that what feels like a long, gentle trend from the inside can conceal fast steps when viewed from above. For our ancestors, the sudden warming was an opening, a chance to expand, to plant, to build, to stabilize new ways of life born under pressure. For us, looking back, it is also a mirror, showing how delicate some of the balances we now depend on might be. As we trace those ancient shifts and the paths that people took through them, we come to the final question. Given all this evidence, what can we actually say for sure about the Younger Dryas, and what still lies in the realm of open mystery? When we pull all these threads together, a few pieces of the Younger Dryas story stand on fairly solid ground. We can say that there was a sharp North Atlantic centered cooling near the end of the last ice age. In Greenland, the temperature signal drops hard and fast. In northern Europe, tundra and steppe plants rush back in. In the North Atlantic Ocean, surface waters freshen and chill. This wasn't just a minor wobble on top of a smooth warm-up. It was a distinct step backward toward glacial conditions in one of the most climatically influential regions on Earth. We can also say that the oceans almost certainly played a central role. The weight of evidence points to a significant change in the Atlantic meridional overturning circulation. Deep water formation patterns appear to have shifted. The chemical fingerprints of water masses in marine sediments change. Plankton communities reorganize in ways that line up with weaker northward heat transport. In that sense, the Younger Dryas looks very much like an experiment the Earth system ran on itself. What happens if you turn down the North Atlantic heat pump during a time of overall deglaciation? The answer, at least regionally, is abrupt cooling, altered storm tracks, and a cascade of ecological and human responses. Beyond that core, the picture becomes more tentative. We have several plausible triggers for the circulation change: large pulses of meltwater from retreating ice sheets, especially in North America, a natural reconfiguration of ice-dammed lakes and drainage routes, perhaps even a sequence of volcanic events or subtle changes in solar output that helped nudge the system. There is also the controversial impact hypothesis, which proposes that fragments of a comet or asteroid exploded over or onto the ice sheets, darkening surfaces, injecting debris into the atmosphere, and triggering wildfires. Some sites do show unusual layers of microscopic spherules, nanodiamonds, and elevated platinum, which proponents link to such an event. Yet none of these ideas fully closes the case. Part of the problem is timing. To really test a trigger, we need to know exactly when it happened relative to the cooling. That means matching up dates from ice cores, lake sediments, marine cores, cave deposits, charcoal layers, and archaeological sites, each with their own quirks and uncertainties. Radiocarbon ages need calibration. Layers can be disturbed by burrowing animals, by ice flow, by erosion. Different archives have different resolutions. Ice cores might resolve individual years. Some ocean cores smear centuries together. When scientists try to line these records up, small errors in each can add up. Did the meltwater pulse start a century before the cooling, or a century after? Did the purported impact debris fall just as temperatures dropped, or slightly later? Right now, those questions don't always have clean answers. Regional complexity adds another layer of uncertainty. The Younger Dryas signal is strongest around the North Atlantic. Elsewhere, it can look muted, delayed, or even inverted. Some tropical records hint at cooler conditions. Others emphasize shifts in rainfall rather than temperature. In the southern hemisphere, the pacing can be offset. Any trigger that claims to explain the event has to account for this patchwork of responses and lags. And our proxies themselves, as powerful as they are still indirect. Oxygen isotopes, pollen grains, tiny shells, magnetic grains, rare elements, they each tell part of the story, filtered through biological and physical processes we do not completely understand. Models, meanwhile, are simplified versions of the climate system. They can show us how a freshwater pulse might slow the overturning, or how volcanic aerosols might darken the sky, but they don't yet capture every nuance we see in the geological record. The good news is that this picture is not frozen. Every decade, chronologies improve, ice core dating gets tighter, radiocarbon calibration curves are refined. New methods, like counting annual layers in lake sediments, or using trapped gases in ice to synchronize records between hemispheres, sharpen the timeline. More sediment cores are being drilled from critical regions. The pathways where meltwater would have flowed, the deep basins that record overturning strength, marginal seas that feel every twitch of ocean circulation. High-resolution analyses can now trace seasonal to decadal changes where we once saw only broad smears. Climate models are also evolving. Higher resolution, better physics, more realistic representations of ice sheets and freshwater flows. Researchers can run ensembles of simulations, testing thousands of combinations of meltwater, volcanic forcing, and internal variability to see which best match the proxy records. Over time, this kind of work will likely whittle down the list of viable triggers and clarify which mechanisms were central and which were supporting players. So the Younger Dryas story is both reassuringly concrete and humblingly open. We know there was a rapid cooling centered on the North Atlantic. We know the ocean circulation changed. We know ecosystems and human societies were reshaped by that shift, and that its abrupt end opened the door to the Holocene world we now inhabit. But we don't yet know exactly which thresholds were crossed in which order, or how close the system came to choosing a different long-term path. We don't know whether a single dramatic event, or a cluster of smaller ones, provided the final push. We don't know how many similar near misses may have occurred in Earth's deeper past, unrecorded in the archives we've sampled so far. Lying here with this story in your mind, you can imagine Earth's climate as a set of balances, always adjusting, sometimes gently, sometimes with a sudden tilt. A little more fresh water here, a little less sunlight there, an ice sheet shifting its weight, a circulation cell weakening or strengthening. Most of the time the system absorbs these nudges, but every so often it tips and a new pattern emerges. The Younger Dryas is one of those moments when the balance shifted, and then shifted back. It reminds us that the relative calm of the Holocene is not guaranteed by any cosmic rule, but is instead the outcome of a chain of accidents and feedbacks, thresholds crossed and thresholds avoided. A reminder of how finely poised some of the conditions we take for granted really are. If you've drifted with this story all the way to here, and you'd like to help more people find it, you're welcome very gently to tap like or subscribe for more quiet journeys into deep time. If you feel like sharing, you can leave a comment about where in the world you're listening from tonight. Those scattered points on the map, all of us living on the far side of an ancient cold snap, are part of the same unfolding story the Younger Dryas helped to write.